In this video, let us study more about correlation. Let us see about the orthogonality between x and y. We can say that two random variables x and y are orthogonal if the covariance of xy is equal to minus of mu x mu y. If in an application, if the correlation is zero, then we know that expectation of xy is equal to 0. For two independent random variables x and y, we can write expectation of x to the power n, y to the power n is equal to double integral x to the power n, y to the power n, the fx of x, fy of y dx is y. To separate the x and y, so we have integral of x to the power n fx of x dx, integral of y to the power n fy of y dy is equal to expectation of x to the power n, expectation of y to the power n. In case of uncorrelated random variable, the value of n is equal to m, that is equal to 1. We can make a general statement here that whenever we say that two variables are independent, that means they are uncorrelated to each other. Correlated x and y. We define the correlation coefficient as rho xy is defined as rho xy is equal to covariance of xy divided by sigma x sigma y in the denominator. Dividing the covariation by two standard variations, sigma x and sigma y are the standard variations, the size of the correlation coefficient can be found. And expectation of x minus mu x divided by sigma x plus or minus y minus mu y sigma y whole square will be always greater than or equal to 0. It should be always positive. By expanding the above, we take the square of this term. We get this as x minus mu x divided by sigma x whole square plus or minus 2 times x minus mu x y minus mu y divided by sigma x sigma y plus y minus mu y sigma y whole square should be greater than or equal to 0. We apply the linear operations and we apply the expectation operation. So this reduces expectation of x minus mu x divided by sigma x whole square is equal to 1. Expectation of y minus mu y divided by sigma y whole square is also equal to 1. Now this is equal to rho xy because it is given, this is covariance of xy. The numerator term is going to be the covariance of xy. So this numerator is going to be covariance of xy divided by the standard deviation term. Therefore, we can write this as 1 plus or minus 2 times rho xy plus or 1 greater than or equal to 0. So when we simplify this, we get this as here, this is equal to, it is 2 plus or minus 2 rho xy is it greater than or equal to 0. That means 1 plus rho xy is greater than or equal to 0. So when we take this 1 to the other side, we get the modulus of rho xy should be less than or equal to 1. We consider the deterministic relation between x and y, where we define y is equal to ax plus b. We know that covariance of xy is equal to the expectation of x minus mu x, y minus mu y. So y is given by ax plus b and mu y is given by minus of a mu x plus b. So that will give you minus A mu x minus B. When we further simplify this, we get this as expectation of x minus mu x. B and B will get cancelled out. A is common factor here, x minus mu x. So that can be further written as A is a constant which can be taken out. A times expectation of x minus mu x whole square. That will give us A times sigma x whole square. This is the standard deviation. So therefore it is square of the standard deviation. The standard deviation y is given by plus or minus root of a square sigma x. The correlation coefficient is given by rho xy is the covariance of xy, that is A into sigma x square divided by sigma x into sigma y, where sigma y is given by plus or minus root a square into sigma x. So therefore you have this as in the denominator plus or minus root a square sigma x square. It will get cancelled out, so we get the answer as plus or minus 1. We consider the figure shown here. Here the bivariate period is defined as 1 for all values of x varying between 0 to 1 and y between 0 to 1. So this is the area under consideration where bivariate period is going to be 1. Let us find the PDF for x. PDF for x is given by fx of x, that we can get by integrating the PDF with respect to y between the limit 0 to 1. So we get this as 1 for all values of x between 0 to 1, and it is 0 otherwise. Similarly, we can obtain the PDF for y. Fy of y is equal to integral of 1 with respect to dx, that is PDF with respect to dx, and here we know that x value varies from 0 to 1 for all values of y varying between 0 to 1, and it happens to be 1, and for values of y varying between 0 to 1, and it is 0 otherwise. So when we multiply these two, fx of x and fy of y, we get 1 for all values of x varying between 0 to 1, y between 0 to 1, and it is 0 otherwise. Let us try to find out the mean mu x and mu y. Mu x is given by the integral of x fx of x dx, and fx of x is found to be 1. So therefore it is integral of 0 to 1 x dx. When we simplify and substitute, we get the answer as half. In the similar way, we can find out mu I. It happens to be half. The correlation of x and y is the expected value of the product x and y. So therefore, E of xy is the integral of minus infinity to infinity, integral minus infinity to infinity xy, fxy, x comma y, that's the bivariate period, dx dy. Here we know that x value varies from 0 to 1, y also varies from 0 to 1. It is xy. fxy is going to be 1 into dx dy. When we simplify this, we get the answer as 1 by 4, that is equal to mu y mu x. Because mu y we have got it as half, mu x also half, half into half, that gives you 1 by 4. Since now we can observe covariance of xy is equal to expectation of xy minus mu x mu y. But here expectation of xy is given by mu x mu y. So therefore they get cancelled out. It turns out to be 0. Since covariance of xy is equal to 0, we can say that random variables are uncorrelated. Let us take the next example wherein we have defined the bivariate behavior as shown in the figure, and fx of x and fy of y are defined here, and we can find out the mu x and mu y. Mu x is given by integral minus infinity to infinity x into fx of x dx. That will give us half. Mu y is equal to integral of minus infinity to infinity y into fy of y dy. That also will give us half. Next step is to find the expectation of xy, and we know the equation. It is double integral xy the pdf dx dy. When we simplify this, we get the answer as 1 by 4, that is equal to mu x mu y. We also know that covariance of xy is defined as expectation of xy minus mu x mu y. In this case, expectation of xy is mu x mu y, so they get cancelled out. Covariance of xy becomes 0. With this, we can say that the random variables x and y are uncorrelated. Let us move on to the next example where the bivariate random variables x and y parameters are given to us. Mean f is 1, standard deviation squared of x is 2, and mu y is 3. Sigma y square is equal to 4. Correlation coefficient is rho xy is given as 0.5. We need to find the values of covariance of COV and also the correlation expectation of xy. The correlation coefficient is given by the ratio covariance of xy divided by sigma x sigma y. It is given as 0.5, and sigma x is √2, sigma y is 2. By simplifying this, we get covariance of xy is equal to 1.4142. The covariance of xy is also related to expectation of xy as expectation of xy minus mu x mu y, that is equal to 1.4142. By simplifying this, we get the expectation of xy is equal to 4.4142. Thank you. In the next video, let us study transformation.